And I continue. Okay, so these are Paul's notes, and I'm continuing by hopefully today completing partial fractions. Problem 1. Okay, so I'm to determine the partial fraction decomposition of this. So I factorize the denominator to obtain x minus 5 times x plus 3. And the numerator is just fine as it is. And the objective is to turn it into a over x plus x take 5 plus b over x plus 3, and to find out what a and b are. So if I just add up, so if I just perform the fraction addition algorithm on the right-hand side, then what I would end up doing is this to this numerator, multiplying it by x plus 3. And this to this numerator here, multiplying it by x minus 5. And the final result would have to equal 17x minus 53. So 17x minus 53 would have to equal a plus bx plus 3a minus 5b. And so a plus b would have to equal 17. And 3a minus 5b would have to equal minus 53. So I'm going to multiply the top one by 3. And I'll leave the bottom one alone, the bottom equation alone. And then I'll do the top equation minus the bottom equation. So I'm going to have 8b is equal to 51 minus 53, which is 51 plus 53, which is 104. And if AB is equal to 104, then B must equal 13. And if B is equal to 13, this implies that A is equal to 4. And the full partial fraction decomposition will look like this. If I spell it all out, 4 over x minus 5 plus 13 over x plus 3. And we check. And you can see that's correct. So I'll load up the next two. We'll try the next two. For the next one, we factorize the denominator again. And ultimately, it will end up looking like this. Something like this. All right, let's think. Yeah, so minus 4 there and a plus 2 there. And that will generate that when I multiply these two together, will create the original quadratic down there. And then a times x minus 4 plus b times 3x plus 2 has to equal 34 minus 12x. And the way that I'm going to solve this, instead of doing what I did before, is I'm going to let x equal to 4. And so the first term disappears. And for the next term, we have a 12 out of 2, which makes 14. So 14b. And on the right-hand side, 34 minus 48 is minus 14. So b is equal to negative 1. Then we'll let x equal negative 2 over 3. And that should disappear. And that should stay. So negative 4 2/3 of a. Negative 4 2/3 of a. Which is the same thing as negative 14 over 3 times a. And on the right-hand side, 34 minus 12 times minus 2/3. Negative 12 times negative 2/3 is 8. And 34 add 8 is 42. So this implies that a is 126 over 14, which is 9, but it should be the negative, so a is negative 9. And if you make the substitution up there, that should be right. And so we check. And that's correct, and that's good. Now problem 3. I guess I can sort of just see it here. Yes. For problem 3, we have oh, I see. Okay, so they've already factorized it for us. So we're looking for a over x minus 1 plus b over x plus 3 plus c over x plus 4, such that when you add them all together, you recover their original rational expression right there. So how would this work when I actually do the addition? I would end up doing a times x plus 3 times x plus 4 plus b times x take 1 times x plus 4 plus c times x minus 1 x plus 3. And all of that would have to equal 125 add 4x take 9x squared. And so the way that we're going to think about this is we're going to make simple substitutions for x. If we were to expand that out, then we would get 3 simultaneous equations in 3 variables, which you could easily solve with a matrix, Cramer's rule, and all that good stuff. But I think it's much simpler to just say let x equals negative 3. Let x equal negative 3. Then the first and last term cancel out on the left-hand side here. But up here we have negative 4 times 1, which is negative 4. And so negative 4b is equal if I then pick up -3 and put it in there, I'll have 125 take 12, 125 take 12, take 81, which is 125 take 93, which is 32. So b is -8. And then if we let x equal -4, the first and second term on the left-hand side vanish, and the third term becomes (5c). So 5c is equal to, let's see, 125 take 16 take 36. So that's 125 take 52 Uh-oh. Not getting the whole number. Alarm bells are going off. Alright, so try again, I guess. First and second terms do vanish, but we're going to have -5 times -1, which is indeed 5c. 125 take 16 is 109, and then that would be 109 take 36. 109 take 36, which is the same thing as 100 take 27. So that'd be 63. So I do think that in fact C is 12 3/5. Or to put it another way, 63/5. And then finally let x equal 1. Just simply 1. In that case, the second and third terms vanish. And the first term becomes 4 times 5 times a, which is 20a. And the right-hand side becomes 129 minus 9, which is 120. So a is 6. And if you put those in the correct spots, that should work. Or so I hope, or so I believe. Let's see. Okay, so 6 and 8 work for A and B. But how come C is not what I thought it would be? How come? I dropped something? Let's reconsider. Okay, those two in the right spot. And then we have those two. And then those two. And then yes, that side matches. So it must be that I've evaluated that incorrectly. First and second term do vanish. -4 minus 1 is indeed -5. That would indeed be 5c on the left. So unless we get 35 on the right somehow and I just haven't seen it. 124 minus 16. Oh no, the squaring of negative 4, that should be 16, and 16 times 9 is 144. And 144 minus 16 is minus 160, and we take that away appropriately, and it's actually negative 35. So that was the minor arithmetic error. I'm glad we caught it in the end. It certainly didn't feel right. Wait, was it 35 or negative 35? Oh, negative 35. And therefore C should be negative 7. Yeah. Okay, so that's good. Now on to problems 4, 5, and 6, which feature repeated factors in the denominator. So for problem 4, how is this going to look? Well, let's think. So we've got 10x at 35 over the square of x at 4. And we want that to be equal to that plus that. And let's see now. That will have to equal that. And so we're going to get what on the left? X squared, so 8a plus b. And then 16a plus 4b. And that will have to equal this. So I mean, I have to be doing it wrong. I just have to not be seeing it correctly. Oh. So let's just think. Instead of looking at the notes, let's think. What do I do? Times that by 3 and that by 3. And I don't do anything to that. That's how I get the other side. Okay, so here's what I think is really going on now that I've refreshed my memory. I think it's really a case of this plus this. And so then we learn that A has to equal 10 and B has to equal, no, just a sec. And then 4A plus B has to equal 35. Therefore, B has to equal negative 5. put those in the right spot, I should get the right answer. So let's check it out. And then afterwards, we'll do problem 5 right here. Okay, so that's correct and that's good. Okay, now problem 5. Let's see. So it should be more or less the same, right? We have 6x add 5 all over 2x take 1 all squared. And we're decomposing that into this partial fraction plus this partial fraction. And just like when we add, 5 over 3 plus 2 over 9, for example, I could just follow the standard routine to add these, 5 times 9 plus 3 times 2 over 3 times 9, that one. Or I could be intelligent about it and multiply the top and the bottom by 3. And then they have a common denominator, and then I can add them. So the same thing happens up here. I multiply the top and the bottom of this by 2x minus 1. So what does that mean? That means that a times 2x minus 1 plus b has to match and equal the numerator of this. Like that. So what do we conclude when we match the pieces together? We see that 6 must equal 2a. So a is 3. And negative a plus b is equal to 5. Now we pick up the 3, we put it in there, and we say negative 3 plus b equals 5, and therefore b is equal to 8. And we put them in the correct spots, and that's correct, and that's good. Problem 6 now. Problem 6. Okay, 7x squared minus 17x plus 38. So I'm going to visualize a over something plus b over something, c over something. But what is going to be in these positions? X minus 1 squared will be there. X minus 1 will be there. And x plus 6 will be there. Okay. Then when I add these 3 fractions intelligently, like using the lowest common denominator, a will end up being multiplied by this. B will end up being multiplied by this. And C just by x plus 6. And now if you expand it all out, well, you can expand it all out if you wish. Let's just think. Here's a better idea. That x equal negative 6. If x is equal to negative 6, then the second and third terms will vanish. And the first term will stay. So negative 6 minus 1 is negative 7. Negative 7 squared is 49. So the right-hand side turns into 49a. And on the left-hand side, what's 7 times the square of negative 6? That would be 7 times 36, which is 252. What's negative 17 times negative 6? That's positive 102. And then plus 38. 252 plus 102 plus 38 makes 354 plus 38, which is 392. And that's 8 times bigger. So A must equal 8. Now, what if we were to let x equal to 1? That's a good idea. If we set x equal to 1, then the first and second terms on the right-hand side vanish. And we end up with just c times x plus 6, which is c times 7, or 7c, on the right. And on the left, you have 7 minus 17, which is minus 10. And minus 10 plus 38 is 28. So c must equal 4. And the last one we have to figure out is b. So we've already used this strategy to get a and c, and it doesn't these to disappear. So I guess what we need to do now is I can't really see a way around it. I think we're actually going to. But the good news is A is known to be 8 and C is known to be 4. So it's not that bad, right? So on the right-hand side, I guess I'll end up with x squared minus 2x plus 1, or 8x squared minus 16x plus 8. And here, wait, do I actually necessarily have to do this? Just thinking. Okay, so I have the 7x squared on the left. And here's where I'm going to get an x squared term from. And it's going to be bx squared, isn't it? And I don't really care so much because I know the 8x squared here and the bx squared here are going to come together. And we're going to get 7x squared. And therefore, b is 1. And so now we must check. Now we must check. Okay, so that's exactly what I wanted. 8, negative 1, and 4. And that's good. All right. The 7th problem. I guess it has the same format as problem 6, but is there any difference I detect? Not so much. I think it's essentially the same, but I might get tripped up. Who knows? All right, so I'm visualizing what I did earlier. And what is it over? 2x at 3, x take 2, and x take 2 all squared. And so that will fit my a term. That will fit my b term. And my c term will have this. Okay. So first I'm going to let x equal to 2. And so the first and second terms on the right-hand side vanish. And I have 7c. And on the left, 4 times 2 squared, take 22 times 2 plus 7. 4 times 2 squared is 16. Then 16 minus 44. Minus 44 is minus 28, right? And then minus 28 plus 7 is minus 21. So C is equal to negative 3. Oh no. Okay, so I guess the next thing I should try is to let x equal whatever causes this to disappear. And the answer to that is 3 over 2. Negative 3 over 2. Negative 3 over 2. So the second and third terms on the right-hand side vanish. And then you have negative 3 over 2. Take away 2, which is negative 3.5. Which is negative 7 over 2. Isn't it? Negative 3.5. Yes, that's negative 7 over 2. But that has to be squared. Okay, so 49 over 4. I better get a whole number out of this. Otherwise I'm gonna be pretty okay, so wait. What's negative 3 over 2 squared? 9 over 4. Times that by 4, I get 9. What's negative 3 over 2 times 22? And plus 7. So 49 equals 49 over 4a. Okay. So what, a is equal to 4? I think that's right. And now the last one. B. So I'm going to do what I did before. So for B, special strategy. I pay attention to this. And the squared, x squared term I get from this times a. And then the 2x squared term from this I get times b. Yeah. So 4x squared equals ax squared, which I already know. So 4x squared, I beg your pardon. Let's just take 4x squared. Oh no. Uh-oh. That's not going to work, is it? Or maybe it will. Does this mean that b is equal to 0? Better not risk it. Okay, we'll try the linear term. Okay, what do I get? Minus 4x times a, so minus 16x. Minus 16x, and then over there with the c, that'll be minus 6x. So that's two pieces of evidence that b is actually equal to 0. So I think that this term here actually does not exist. Now you end up with this plus this with a 4 on top. And a negative 3 on top. That's what I think. And so now it's time to check. Everything must be checked. And that's correct, and that's good. That's awesome. And now for the 8th problem. If I apply b squared minus 4ac just for no reason really at all, I get 49 minus 12 times 28, which is going to be negative, so it's not factorable and it doesn't have real solutions anyway. But that doesn't really tell me anything. And I know that x squared at x at 7 is not factorable anyway. So what do I do? Just proceed like normal and see what happens. So I'm visualizing this. And so let's see what happens. Okay. Well, that would imply that a is 3 straight away. But if a is 3 and a plus b must equal 7, wouldn't b be equal to 4? Indeed, yes, that's right. So I believe that there will be a 3 there and a 4 there. Seems too easy, seems too simple, but the only way to find out is to Check. No, it's incorrect. Okay. Okay. But don't look anymore. Think about why is it incorrect? Okay, so first, let's just see if this would even work anyway. The 3x squared, that's fine. Then 3x and 4x, that's fine. Get 7x. Then 21, which is not 28. So you actually need something else here. It will go on top of here somehow. Oh. Hmm. Somehow like a corrective plus C somehow. Just like that? Just like C, just like that? I really don't know. I do understand why what I originally believed was false, but I don't understand how that fixes it. So I have to look at the notes. All right. It's like that, is it? All right, okay, fine. So it must be fixed. Decompose that partial fraction into a pair of pieces like what? Like this and this. That's a 7 there, by the way. So what? Okay. And A plus C and 7A would have to equal 28. Well, that straight away implies that A is equal to 4. And if A is equal to 4, then C must equal to 3. And C is equal to 3. Rather, if A is equal to 4, then B must equal to negative 1. So it's a negative x plus 3 and a 4 there, right? Tell me that's right. Yes, that is right. Okay. How to do the 9th problem? It's the same, isn't it? But it just so happens that little b is equal to 0, right? I get it. I think I get it. What we're about to see. Okay, so ax plus b over x squared plus 4 plus cx plus d over x squared at 4 times all squared. Like that. Right. Right. So 4x cubed at 16x at 7 is equal to that times x squared at 4. Plus just that. Now, expand on the right. So ax cubed plus bx squared plus 4ax plus cx. So plus 4a plus c times x plus 4b plus d, I believe. And this has to match up with this. So straight away, this tells me that a must equal 4. And it tells me that b must equal 0 because of this. And if b is equal to 0, then d must equal 7. And finally, if a is equal to 4, 4 times 4 is of course 16. And 16 plus c has to equal 16 itself. So I think c is 0 as well. So is it the case that this is 4x over x squared plus 4 plus 7 over x squared plus 4 all squared? Seems like it, but seems unlikely. We're about to see. No, that's correct, and that's good. That's brilliant. Okay, so it says 7 to the 5 is 16,807. Express it in logarithmic form. Okay, log base 7 of 16,807 equals 5. Number 2, 16 to the 3/4 equals 8. In logarithmic form, I would say log base 16 of 8 is 3/4. And third, it says 1/3 to the negative 2 is 9. To put it another way, the logarithm base 1/3 of 9 equals negative 2. And we check if those are correct. First one is right. Second one is right. And the third one is right. For problems 4 to 6, write these in exponential form. So those were in logarithmic form and now in exponential form. So I say 2 to the 5 is 32. Log base 2 of 32 is 5, so 2 to the 5 is 32. Log base of a fifth, log base 1/5 of 1/625 is 4, so I say 1/5 to the 4 is 1/625. Problem 6. 9 to the negative 2 is 1/81. And now we check those to make sure they're correct. That's correct. And that's correct. And that is 2. And that's good. Now, for these next ones, we must determine the exact values without using a calculator. Very well. Log base 3 of 81, that would be 4. Log base 5 of 125, that would be 3. Log base 2 of 1/8, that would be negative 3. Log base 1/4 of 16, that would be negative 2. Yes. Right? Because 1/4 to the 2 is 1/16, and to the negative 2 is 16/1. Ln of e to the 4, that would just be 4. Log, as in common log, of 1/100th would be negative 2. We're going to check all these. Absolutely everything must be checked. Because without checking, there is no computing. So that's correct. And so is that correct? Correct. Correct. And finally, that's correct, and that's good. Okay, next. Write each of the following in terms of simpler logarithms. How to do the 13th one. First, we're going to use this law, that if you're multiplying a pair of things together, then you can separate it out. And in fact, if you think about it, I'm doing 3 times x to the 4. So really, I could rewrite that. As log base 3 plus log base, as log of 3 plus log of x to the 4 plus log of y to the negative 7. Then, if you think about it again, this x to the 4 business is like log of x times x times x times x. So really I'm adding all those together. So in other words, it's 4 copies of those. So in other words, this 4 comes right to the front. So log 3 plus 4 log x minus 7 log y. And we check. And that's correct. Great. Next up, ln of x times the square root of y squared at z squared. Okay. First, pretty confident that it's ln of x plus this. Then, I think that there's nothing you can do. Personally, I think there's nothing you can do. It's very tempting to think there is, but I don't think there's anything you can do. And that's good. He agrees. Great. Now for the 15th one. Log base 4 of this quotient right here. I just feel very fancy saying the word quotient. It's just a fraction, isn't it? So it's that. Take away that. But wouldn't that be log base 4 of y squared plus log base 4 of 5th root of z? I think it would. So I'm going to try and get to the end in one step. Whoops. There. And then notice that that should be in like brackets, right? So if I do split it up and put it as 1 log plus another, it would ultimately be minus log minus log. So I think that the answer is this. And so we will check. And that's great. Okay. Now for the 16th problem. Combine each of these into a single logarithm with a coefficient of 1. All right, that 2 would come up there. That 5 would come up there. That half would turn that into a square root. And then I'm dividing everything. So I think that the answer is this. I think it's x squared y to the 5, and it's all divided by the square root of z. That's what I think. Better make sure I understand it. Okay, great. That's true. For the 17th one, that will cube the t plus 5. That will raise the t to the power of 4. And in fact, let's just do this. Wait, I didn't see that. Uh-oh. Just a second. Okay, is that fine? Right, okay. What happens to this? Oh no, it's not a minus sign there. I did it in the wrong spot. All right, so t to the 4 like that. And then that would be plus, right? So it'd be like that. And then like that. And that's good. That's great. All right. Problem 18. Okay, that's the cube root of a. That's what that third is going to do. That's going to raise that to the power of 6. And I know what this is. This is log of 100, isn't it? Secretly, it's log of 100. So just to make everything work for me, I'm going to do this. Like that. And in fact, just to line it up in my mind, I'm going to do this. Well, I can barely see it. Yeah, like that. Okay, now let's do it. 100 cube root of a all over b to the 6. How about that? Hooray! Great. All right. Problem 19. 19 just sounds bigger than the number 20, doesn't it? For no reason. Like, imagine being told you have to run 19 miles, but 20 sounds like, no, you know, it sounds like I could do that, right? So use the change of base formula and a calculator to find the value of each of the following. Okay, so how to remember the change of base formula, right? the way I think of it is, pretend that you only have this button or this one on your calculator. You don't have the fancy custom logarithm button anymore. It's forbidden. How can you still do it? How can you work out this using just these two buttons and the other arithmetic ones? Okay. So like, I know that log base 2 of 8 is 3. And I know that for log of 8 and log of 2, the bigger one is 8. So this helps me get it the right way around. Like that. So I think that this is log 35 over log 12. And then I have to use a calculator to actually check if that's true. And I get about 1.43, which is right, about right, is it not? Because 12 to the 2 is 144, so it should be between 1 and 2. And then for this one, I mean, it's just really just the same, isn't it?